So now, let's go into the software for a hands-on demonstration. So let's take a look at SOLIDWORKS CAM now. And SOLIDWORKS CAM is fully integrated into SOLIDWORKS and is in every seat of 2018 or later, currently on subscription. And I'm going to be using the SOLIDWORKS CAM Standard to program this part model. You can see this is a timing cover for a V8 motor. And so I'm going to go ahead and program this. We're going to suppose that we are going to manufacture this out of 6061 T6 aluminum. And so what I'll do is go here, and once SOLIDWORKS CAM is activated, and you can find it under add-ins, here's the SOLIDWORKS CAM 2024, which I'll be using. And once it's activated, then there are some tabs that are added to the command manager. You can see these tabs up here, and I'll be using the SOLIDWORKS CAM tab. And there's also 3 tabs that are added to the property manager. So one for the tools, and you can see I have a default machine selected as a Haas VF3, and I have some tools pre-assigned here. These might be common tools that I use on that machine often, and so I have those already pre-assigned in my tool crib. And then there's also a tab here for the SOLIDWORKS CAM operations and a tab for the SOLIDWORKS CAM features. So we're going to be using feature-based programming here to program this part. And I'll start by extracting the machinable features on the part. And so this will use automatic feature recognition to recognize all of the features on the part. And it will add those features to the SOLIDWORKS CAM feature tree automatically for us. So you can see all of the features here. This part would require 2 setups, one from this side of the part and another from this side of the part, since we have some features here as well. And so you can see the SOLIDWORKS CAM feature recognition has automatically created a facing feature, a part perimeter feature, open pocket feature for this raised island in the center here, and then various irregular pockets here, for example, for the machining of the part, and circular pockets as well for these circular pockets. So all of these features have been defined automatically for us and added to the feature tree. I might also mention that as far as the holes go, SOLIDWORKS CAM looks at all of the holes and recognizes tapped holes from the hole wizard. And because all the holes are identical, it groups them together and processes them together. And same thing with the M6 holes, threaded holes here as well. And so these have been grouped together automatically. And likewise for just drilled holes. So if there's drilled holes in the part, it will also create groups automatically for those, for the different sizes of drilled holes. Now that we have recognized all of the features on the part, we can generate the operations for machining. And this will use the patented technology database to generate all of the operations for machining. And you can see these operations here. And then go ahead and generate the toolpath. And of course, using that technology database, you can capture your best practices and you can decide how you want to machine the different features on different parts in different materials and store that knowledge into the technology database as you're programming so that it can be then reused automatically. And that's what I've done here as well. And I'm creating the toolpaths now for machining here. So it's created all those toolpaths for us now. And if I go ahead and simulate, we can now see the machining of the part. I might also mention that I had a piece of stock predefined as a bounding box with a couple millimeters on either side of the part, and 5 millimeters underneath the part to hold the part in a vise for machining. And you can see now that the toolpath simulation is complete, and I can compare the machined model to the design model using this button. And you can see the comparison here on the upper left, and everything is in green, is net to the design model. If there was any gouging that occurred, it would be in red. And if there was any remaining stock, it would be in blue. And you can see pretty much everything is green here. There is a little bit of yellow on some of the tapped holes. That's a result of them being modeled as the drill tap size rather than the major diameter of the thread. And if we look at the opposite side, everything is in green and looks really good here. So we have machined the part net to the design model. Okay. So very quickly, I'm able to generate CNC programs for parts like these. And let me also mention, I can also go back to the feature tree for a minute, and I might want to do a little engraving on the back of this surface here. So let me add that feature to the second setup here, the second side. And what I'll do is create a 2.5 axis feature, which is a curve feature. And I have a sketch of what I'd like to engrave on there. You can see the CamWorks engraving here. I can put the end condition. How deep do I want to engrave? I'll just say 0.2 millimeters. I just want to scratch the surface, so to speak. So I'll go ahead and put that in, and then generate the toolpaths for operation and toolpaths for that as well. So let's generate the operation plan and then generate the toolpaths here. And then we can go ahead and do the machining one more time here. Flip it over so we can see the first side being machined, the first setup. And each of these setups can have a different work offset number. I could also generate 2 different programs for these 2 setups if I want to do that. And you can see here where I've done the engraving now as well. Yeah. All right. So very easy to program parts, 2.5 axis prismatic parts, 3 axis parts using the SOLIDWORKS CAM. And this is just the SOLIDWORKS CAM Standard that you're looking at here. So now let me go ahead and generate the G code for machining. And I can give the file a name and then go ahead and generate the code for machining the part. Okay. Now I've been able to program this part in less than 10 minutes. And you might ask yourself, how long do you think it would take to program this part using your CAM system? So that's SOLIDWORKS CAM Standard, and thank you for watching. Next, let's take a look at how SOLIDWORKS CAM can be used to program 3-axis parts like this part. Okay, so now that we've seen how SOLIDWORKS CAM can be used to program 2.5 axis milling parts, let's take a look at how it can be used to program a 3-axis part like this one. This is a shifter for a classic car, a pistol grip shift, and we're going to be using SOLIDWORKS CAM Standard to program this part. SOLIDWORKS CAM Standard is included in every seat of SOLIDWORKS 2018 or later, currently on subscription. So we can go ahead and use it to program 3-axis parts as well. And here I'm going to go to the SOLIDWORKS CAM tree to begin with, the SOLIDWORKS CAM feature tree. And I have a machine that's been selected by default. And then I'd like to take a closer look at the stock manager here and different ways that we can define stock. So let me open up that stock manager. And you can see by default, then SOLIDWORKS CAM uses a bounding box to define the stock. I can also add some stock around that bounding box. I can add it either manually by typing it in, or I can load some default settings that I have. This will add 200 thousandths in X and Y around the part, then 50 thousandths to the top of the part and a 1/4 inch to the bottom of the part to hold on to in my vise. And so now you can see here at the bottom that is close to a nominal stock size or stock sizes, but not really what I want. So the next selection here up at the top, and I could adjust these offsets if I wanted to get an exact size, but instead, why don't we go to the predefined library of stock sizes that we have here. And here I have a 2-inch by 6 1/4 by 1 1/2 inch block that is a standard stock size. So using this selection in the stock manager, you can create your own library of standard stock sizes and then reuse those stock sizes whenever you'd like to save time when you're defining the stock. So now I have a standard stock size selected. I might also want to offset the part a little bit within that stock. So I'm going to put in here that I'd like to offset at 0.1, and actually it's minus 0.1 down so that I have a little more to hold on to in my vise at the bottom, and I still have enough up at the top for the facing. Another way to define stock is using an extruded sketch, a SOLIDWORKS sketch. So if you have an odd size blank, you can make a sketch of that in SOLIDWORKS and then extrude that sketch to create the stock. We can also create cylindrical stock. So if you have cylindrical stock that you might want to make a part out of, you can use cylindrical stock as well. And then there's also STL. So if you've machined or programmed a part on one machine and you want to use that pre-machined part on the next operation on a different machine, you can select that STL file here using this selection. And then you can also just create a SOLIDWORKS part file and use it as stock as well. So a lot of different options here for how to define stock. We're going to be using that standard stock size that we talked about. So let's say OK, and we'll go ahead and proceed. So now that we have our stock defined, let's go ahead and select the coordinate system and take a look at how coordinate systems can be set. So we can use this coordinate system as our part program 0. And you can see here I could use a stock bounding box vertex if I'd like to do that. For example, I could pick one of these vertexes, and that's where the G54 or part program 0 could be set at the center of the block, for example, or the upper left corner, which is common. And we can also adjust the direction of X and Y here as well. For example, I could flip X and Y if I want to do that. Once we have the coordinate system we want, part program 0 we can say OK. And now that but we have both the stock and the part program 0 set, and you can see it there. Okay, so now what we can do is create a new mill part setup. This is a new setup for the direction of where we'll be machining from, and we're going to be machining in this direction. You can see the red arrow is pointing in the Z-axis direction of machining. So I'm going to select that there. And then we'll go ahead and say OK, and then create a facing feature. So we need a feature to face this off. And I'm going to go ahead and create a face feature here. Just select the top of the part. For the end condition, the default is up to stock, which is what I'd like. So I'm going to say OK here. Now I have that facing feature. I can also go ahead and create a new multi-surface feature for machining the 3-axis part. So in this case, there's several options again, but what I'd like to do is create a multi-surface feature of all displayed. And then what I'd like to do also is select a strategy for machining, and there's lots of predefined strategies. I have one predefined for cutting this type of part called the pistol grip shift strategy, and it has a couple of tools here. One is a 3/4 inch M mill for roughing, and the other one is a 1/2 inch ball nose M mill that will be used for finishing. So I'm going to say OK here. And now I can go ahead and generate the operation plan for machining and also generate the toolpaths for machining as well. So very quickly, I can create a CNC program right inside SOLIDWORKS to machine this pistol grip shift that I would like to manufacture. And it's going ahead and creating those toolpaths now, and it's finished here. And now we can go ahead and simulate the toolpaths. And here I could use standard simulation, you might say, that where it will show us the tool, and I can set the number of moves and how often it shows us that tool. Let me set it to 1, for example, which is showing us each and every move of the roughing as it goes through and roughs the part. But I can also back up here and just use turbo mode for simulating this type of part. And this works well, particularly for 3-axis parts, because of all the toolpaths that are involved in machining a part like this, especially with the ball nose M mill, trying to get a good finish. You have very fine step over. It takes a long time to simulate it. So what I can do instead is use turbo mode, and then I can simulate it to the next operation, for example. So I'll go ahead and say run here, and it'll show me what it looks like after the part has been faced. And then if I hit it again, you can see what the part will look like after it's been roughed. And then we'll say hit it once more, and now we can see the 3-axis machining, the ball nose M mill, going around and machining the part here. And so we can let it proceed here. And you get an idea of how good the surface finish is here. I have a pretty tight step over on this part that I'm using. And the settings are fairly easy to set in the 3-axis dialogues to be able to create a good surface finish on parts like these. And you can see as it proceeds, it's showing us, it's updating the display every 1,000 moves here. There's a lot of moves here because of the spline sort of shapes that are being created, the curves that are being created here. And you can see it is proceeding as the ball nose M mill goes down and machines the entire part here. I'm going to do the machining. You can see I went about halfway down on this part. We would likely flip this over, put it in some soft jaws, and then do a very similar process to the other side of the part in order to finish this part. And if I use this button, I can display the difference between the machined part and the design model. And you can see that here. And you can see where the blue is stock remaining at the bottom of the part, and the green is net to the design model. Okay, so you can see how it's been machined nicely to the design model to match the design model. Okay. And if I highlight that Z level, you can see the toolpaths that were created by that particular operation and that fine step over that I mentioned there. So very nice toolpaths for machining a part like this. And you can see the vertical lead ins and outs also as well for that toolpath. Okay. And again, it's likely what I do then would be to create another setup, flip it over, and use a similar process to create a program for the second side. Now that I have the toolpaths created, I can go ahead and post-process those toolpaths. So let me go ahead and go to post-process here, give the file a name, and then we can just go ahead and post-process the file. So it'll very quickly create the G-code for the machine, for the CNC machine, to machine this part. And you can see it's already completed the post-processing. And I also have an option here to open that in the SOLIDWORKS CAM NC editor. So if I say OK here, we'll be able to see the actual G-code that would be used for the machining of the part. Now there's one last thing I'd like to show you, and that is how these toolpaths are fully associative to the design model and the advantages of being able to have fully associative toolpaths when a design change occurs. So now let's go over to the SOLIDWORKS feature tree, and we'll edit that freeform shape which makes up this surface that we're looking at here. So let's edit that particular feature. And what I can do is go and select this curve that was used to define the shape of the surface. So let's select it. And then I can move these nodes in order to change the shape a little. So let's move this particular node in a little bit. And we can move these out just a little. And then say OK. And now you can see where the shape of this surface has changed pretty dramatically. And now if I go back to the SOLIDWORKS CAM feature tree or operations tree, let's go back to the operations tree, it knows that the part has changed and asks me if I want to rebuild the toolpaths. So now it will automatically generate and regenerate both the features, operations, and toolpaths to match the new design. And it's able to do that very quickly. You'll see that happening here. And once it's complete, then we now have a program for the new modified part. And if I go to simulate here, this time I'll use turbo mode again and just let it go to the end of the part. So it'll get updated every 1,000 parts or every 1,000 moves again. And you can see that it is now machining the part to the new design change that has been made. So really ideal in terms of saving a huge amount of time in reprogramming with the fully associative toolpaths, and at the same time also ensuring that we're always programming and machining the current revision of the part. So you can see the great advantages of using fully integrated CAD/CAM like SOLIDWORKS CAM and CAMWorks. And the CAMWorks products just adds more capabilities for higher-end machines and also for higher-end 3-axis programming, for example. So there's additional cycles, pencil milling and curve project and other cycles that are added with the CAMWorks line of products. And again, once the part is completely machined here, it's nearly done, then I can go ahead and compare the machined model to the new design model. And we can see that everything is in green and it has been nicely machined to the new design.